students, welcome to the session 12 of the chapter Solutions. Till now in this chapter we have seen different concentration terms and the interrelation between the concentration terms. Okay, now today we are going to discuss a very important topic of this chapter, which is solubility. Now when we talk about solubility, we usually focus about the solubility in liquids in this chapter. But before going to any specific criteria of whether we are talking in solid to liquid, solid in liquid, or gas in liquid, or liquid in liquid, let us keep it very general and understand the term solubility. Okay, in general, what is solubility? Now, if you see the definition, okay, try to understand the definition. Solubility of the substance is its maximum amount that can be dissolved in a specific amount of solvent at a specified temperature. So this is a very properly framed definition. Now let me break this into certain parts to make you understand in a better way. Okay, solubility of the substance. Now I am talking about solubility of a particular substance. Let me or let me take an example of sugar. Okay, if the substance here I am taking it as sugar. Okay, I will take sugar. Now when I take sugar, I am talking about solubility of what here? I am talking about solubility of sugar here. I am talking about solubility of sugar in a specific amount of solvent at a specified temperature. Okay, now what I will do is, I will take a glass, or I will take a beaker. In this beaker, I will take, okay, for example, imagine 700 ml of water. Okay, in this beaker, I have a specified amount of solvent. Here we have to specify the amount of solvent, because in this much amount of solvent, how much solute is soluble. That is the reason we have to be very clear about the amount of solvent and the temperature conditions to why we will see. Now I have taken 700 ml of water. To this 700 ml of water, I will add sugar. Okay, to this 700 ml of water, I will add sugar. Now when coming to the temperature, I will not deliberately, or I will not put any heat source here. So I am trying to keep the temperature constant. Unless and until you do something, the temperature will not drastically change. For example, imagine I am performing this particular activity here in this room. So I will be taking room temperature into consideration. So room temperature will not drastically change, right? Might be in 0.5 degrees Celsius or 1 degree Celsius at this particular point. Here and there, little bit the room temperature will change. But almost I can say it is a specified temperature. There is no temperature fluctuation when I am taking room temperature as my condition. Now at a specified temperature, for now I am taking it as room temperature, which is almost constant. Now for example, imagine now my room temperature is 37 degrees Celsius. At 37 degrees Celsius, I have taken a solvent. The quantity of the solvent is 700 ml of water. Into this 700 ml of water, I'll keep on adding sugar. Now what will happen? The sugar will get soluble in water. Now you keep on adding sugar at one particular point. You cannot add further sugar into the water. Means it has reached a saturation point. What happened here? It has reached a saturation point. What do you mean by saturation point or saturated solution? You have added sugar, you kept on adding sugar. Now you people know water can take only this much amount of water, can take only up to certain amount of sugar. You have studied this in your grade 9. Okay, a certain amount of solvent can take only up to certain amount of solute. Beyond that it can't take. The logic you people know, because in this the solvent particles will have intermolecular spaces. Now whatever solute you are adding, it will go and occupy the intermolecular spaces. At some point, all the intermolecular spaces get completely filled. Now still if you are adding any solute, for here I have taken sugar. Now the solvent will no longer able be take the sugar. So at that point, what will happen? This solution will reach a saturation point. Okay, saturated solution is that solution where you can no longer add any solute. Or it is such solution where the solvent is no longer able to take any more solute. Okay, now at that particular point, when the water can no longer take any sugar, at a specified temperature, with a specified amount of solvent, I am adding certain solute. Now at that particular point, how much sugar is soluble in water is its solubility. Now what can I say here? At the saturation point, at the saturation point. What is saturation point? When no more solute can be added into the solvent. Okay, at the saturation point, okay, when sugar can be no longer, okay, when sugar can be no longer added, okay, the sugar can be no longer added, the amount of sugar, okay, added to the 700 ml of water at constant temperature and pressure. The temperature should be constant and the pressure should be constant. At the saturation point, when sugar can be no longer added, the amount of sugar added to the 700 ml of water at constant temperature and pressure is the solubility of sugar. I hope this is clear for you. Okay, at the point where no longer sugar can be added to the water, okay, at that particular point, how much sugar has been added to the water, at constant temperature and pressure is solubility of sugar. Okay, that will decide the solubility of sugar. Now if I go back to the definition, you can very easily understand. Solubility of the substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. How much amount of substance, okay, how much amount of maximum substance I can add in a specified amount of solute at a specified temperature is called solubility. Here I can add only that much maximum amount of sugar, how much I can add at that, till that point only I will consider the solubility. Okay, till that point. Okay, that is maximum, no? If I have reached a point where no longer solute can be added, means whatever I have added is the maximum amount of sugar. Okay, and the temperature and pressure have to be maintained constant. So now, for example, solubility of sugar. I will take a vague example. For example, I will fix 700 ml of water. Okay, I will fix 700 ml of water as my solvent. Into this 700 ml of water, I can add, imagine, 200 grams of sugar. Okay, so what is the solubility of sugar here? 200 grams I can add in 700 ml of water. Now here when I take glucose, might be I can add 350 grams of glucose. Now it is not like that. If sugar I am adding 200 grams, okay, to sugar I am able to add 200 grams, that doesn't mean glucose also I will be able to add 200 grams only. So the solubility will vary. The solubility is varying, right? For sugar it is 200 grams, for glucose it is 350 grams. Now, okay, so solubility will change. Okay, solubility will change. Definitely it will change. Now, if solubility is changing, on what factors does the solubility depend? Okay, solubility is not a fixed thing. Okay, if you change certain things in the solution, the solubility also will change. What are those things? So for that we can take the, okay, factors affecting solubility. Okay, for that we can take factors affecting solubility. Now when we talk about factors affecting solubility, the first factor affecting solubility is nature of solute. Now for this explanation I have just given, I will take the same 700 ml of water. If sugar I have taken, its solubility will be different. If I change the solute, that solute nature will be different, so its solubility will be different. It will also depend on nature of solvent. For that I can say, for example, I have taken 700 ml of water, so 200 grams of sugar got dissolved. If I change the solvent only, instead of water, if I change my solvent to ethanol, if I change my solvent to alcohol, which is ethanol, then might be, okay, then might be more amount of sugar would have been dissolved. We don't know. Okay, so we can say that if I change the solvent, definitely the solubility of the solute will definitely change. the same sugar, okay, the same 200 grams of sugar, if you take, the solubility of that sugar will differ in water and it will differ in ethanol. So if I change the solvent, definitely the solubility of sugar in water and ethanol will be different. If you take the third one, it is your temperature. And if you take the fourth condition, that is your pressure. Okay, if I change the temperature conditions, my solubility will change. If I change my pressure conditions, my solubility will change. Now, how will temperature and pressure affect the solubility? That we'll see in detail one by one when we talk about solubility of solid in liquid, solubility of gas in liquid. When we talk in individual, okay, as a separate topics, then we will see how exactly temperature and pressure do affect the solubility, because we cannot generalize that increase in temperature will increase the solubility or decrease in pressure will increase the solubility. These are all these are all like they change depending on what we are taking. Okay, they change depending on if the solute is solid or gas. So it depends on various other factors. So these two will be seeing in detail when we further go into specific topics of solid in liquid, gas in liquid. Okay, so on a whole, on what factors does the solubility depend on? Nature of solute, nature of solvent, temperature and pressure. So this is in brief about what is solubility. Okay, what is solubility? It is the maximum amount of substance that can be dissolved in a specific amount of solvent at a specified temperature. Okay, on what factors does the solubility of any substance depend? Nature of solute, definitely, nature of solvent, temperature and pressure. So this is a brief introduction about solubility. Now we are going to see solubility of solid in liquid. How does solid dissolve in liquid? Which kind of solid dissolves in which kind of liquid? How does the temperature and pressure affect the solubility of solid in liquid? So next, let's see that. Now let us discuss about the solubility of solid in liquid. Now, when we talk about the solubility of solid in liquid, okay, we need to talk about the nature of the solid here. Okay, and we should also talk about the nature of the solvent, which is liquid. Because just now I was mentioning, whenever we are talking about solubility, it depends on nature of solute, nature of solvent, temperature and pressure. Now, when we are talking about the nature here, okay, the solid is my solute and liquid is my solvent. Let me little bit talk about the nature of solute and nature of solvent for a better understanding regarding the solubility of solid in liquid. Now, we people know, okay, from a very long time we have this, very much in our minds, like dissolves like. Okay, like dissolves like. Now, when we talk about like dissolves like, what should come in our mind regarding solubility? Okay, now when I take solids, okay, when I take solids, here I have two types of solids here. I have my polar solids. Okay, I have my non-polar solids. Okay, I have my non-polar solids. Now, polar solids. Okay, you people know what are what are your polar solids. In grade 10, you would have studied ionic compounds and covalent compounds. Now, when I talk about the polar solids, I am mainly focusing on the ionic compounds. When I'm talking about non-polar solids, I am mainly focusing on the covalent compounds. Now, you people know when I'm talking about an ionic compound, ionic compounds have cation and anion. So ionic compounds will have charges. So there is whenever you have this separation of charges, whenever you have, even in covalent bond also you have separation of charges, but when it is an ionic bond, you have perfect cation and perfect anion. So they are clear poles, positive pole and negative pole. Okay, so ionic compounds are very strong polar compounds. So solids can be polar solids, which are ionic compounds, and solids can be non-polar solids, which can be covalent. Now, when we are talking about solubility of solids, we need to separately focus on solubility of ionic or polar solids, and we should also focus on the solubility of non-polar solids. Now, when we talk about polar solids, or when we talk about polar solute here. Now then, when we say like dissolves like, we say that polar solids dissolve in polar solvents. We say polar solids dissolve in polar solvents. Now for polar solids here, I am just taking an example of NaCl. You people know Na plus and Cl minus cation and anion exist in this ionic compound. Now when we talk about polar solvents, a very important polar solvent which we know is our water. Now water is a very good solvent, and you people know from your lower grades, water is called as the universal solvent. Now when we talk about water, water is a polar solvent. Water has a very high dielectric constant. Now I am not going into the detailing of what is dielectric constant, but just remember, if a solvent has high dielectric constant, it can dissolve many compounds into it. So water has a very good dielectric constant, so it is a very good solvent, and water is a polar solvent. So water, H2O, is a polar solvent. Now you are getting a doubt, how is water polar? Okay, now if you are getting it out, why is water polar? Because you people know that H2O is a covalent compound. The bonds between oxygen and hydrogen are covalent bonds. But still, when I am talking about a polar solvent, I am talking about water. Because if you see water here, I have already taught you this when I'm teaching when I have been doing the previous concepts. Okay, oxygen and hydrogen, if you have, even in a covalent bond, you have polar covalent bond and non-polar covalent bond. Now if you see oxygen hydrogen bond, oxygen is highly electronegative, so oxygen will pull the electrons towards it, getting a partial negative charge, and hydrogen will get a partial positive charge. The same this side, hydrogen will get a partial positive charge, because though the electrons are shared between oxygen and hydrogen, but the electrons are more moved towards oxygen, so they have the partial charges. So I can talk about polarity here, because they have charges, I can talk about polarity here. So in that way, water is a polar solvent. Now here if you see, you have your Na plus and you have your Cl minus, you have your cation and anion, which are held together by a electrostatic force of attraction. You people know ionic bond is an electrostatic force of attraction. Electrostatic force of attraction is the force of attraction between opposite charges. Okay, it is a non-directional one, so I need not show like a bond. I'll just show some force of attraction. Now this Na plus and Cl minus, when they are put in a polar solvent, which is water, here you have charges, here you have charges. So can I say, here you have charges and here also you have charges. So when I add both of them together, or when I mix NaCl into water, they have same intermolecular interactions. Now here also you have positive and negative charges. Here also you have partial positive and negative charges. So when you put NaCl in water, you have same intermolecular interactions. Now when NaCl sees H2O, H2O will be like, okay, NaCl has charges. Now it will try to surround Na plus and H2O will try to surround Cl minus separately. I am not going into the detailing of this, but if you want to know, Na plus is surrounded by many water molecules, Cl minus is surrounded by many water molecules. That's how Na plus and Cl minus will get separated. Now how is H2O trapping Na plus? Because here positive is there, on oxygen negative is there. So negative can see, this oxygen will attack through oxygen H2O. Many H2O molecules will attack on Na plus and trap it. Through H plus, through positively charged, partial positively charged H plus. Okay, this water molecule will attack on Cl minus, which is negatively charged, trap it and take it apart. Like that, H2O molecules will individually trap Na plus Cl minus and take these ions away from each other. This is how the solubility of your polar solids goes in the polar solvents. Now when I'm talking about non-polar, so this complete thing I was talking about the polar solvents, like dissolves like so, polar solids are soluble in polar solvents. Now when I talk about non-polar solids, okay, when I talk about non-polar solids, okay, they dissolve in, okay, non-polar solids dissolve in non-polar solvents. Okay, for example, here I can take a very good example. Now when I talk about my benzene, okay, when I talk about naphthalene, when I talk about anthracene, okay, when I talk about anthracene, all these compounds, they are your organic compounds. Okay, anthracene are my organic compounds. So when I say naphthalene and anthracene are organic compounds, it means that they are non-polar compounds. So naphthalene and anthracene, if you go about the go into the structure of naphthalene and anthracene, they also have benzene rings. They differ in the number of benzene rings. So naphthalene and anthracene, I can't expect them to be soluble in water because it's a non-polar compound, so it should be soluble in a non-polar solvent. So naphthalene and anthracene are soluble in benzene. Now benzene is not a polar solvent, benzene is a non-polar solvent. Naphthalene and anthracene also are non-polar solvents. Okay, so if you see here, non-polar solids dissolve in non-polar solvent. So naphthalene and anthracene, they are soluble in benzene, but naphthalene and anthracene are not soluble in water. It is a vice versa now. Now if I take sodium chloride and if I put in benzene, definitely sodium chloride will not get soluble in benzene. Okay, why does this happen? Why is this happening? Because if you see naphthalene and anthracene, okay, they are soluble in benzene because naphthalene and anthracene, okay, what do they have? Why is naphthalene and anthracene soluble in benzene? They have similar intermolecular interactions. Okay, they have similar intermolecular interactions. Means what? I'll explain in a very simple way. For example, you take here a beaker. In this, imagine I have benzene. You people know the benzene structure. Okay, so I have many benzenes in this in this container. Now I'm adding naphthalene and anthracene. Now they also have benzene rings only. Okay, they are like this. Okay, they also have benzene rings only. Now the interaction between benzene rings are similar. The interaction between naphthalene and anthracene are also similar. Now when naphthalene or anthracene enter into benzene, they will get in between the benzene. Okay, they will break. For example, they have 2 benzene rings, they have 3 benzene rings. The benzene rings will get separated. Why do the benzene, what I mean to say is, imagine, okay, let's take like this. I have taken a test tube full of naphthalene solution. Okay, or I have taken a naphthalene ball. Okay, I have taken a naphthalene ball because we are specifically talking about the solids. I have taken a naphthalene ball. In that you have some millions of naphthalene molecules. Molecules arranged together. Now, when you put that naphthalene balls into the benzene solution, what will happen? Now, all the naphthalene molecules, okay, 1 naphthalene, 2 naphthalene, 3 naphthalene, all the naphthalene molecules, when you put it in benzene, they will feel like, oh, the solvent in which we are put in, they also have the same interactions between, same interactions, because it is also the similar type of molecules. Now, all the naphthalene molecules will get away from each other and get into the benzene solution. If it was not benzene and if it was water, then what will naphthalene think? Let me not go into the let me not get separated. All the naphthalene molecules will think, let us not get separated and go into the solution because it has some different kind of interactions and we can't go and sustain between a different kinds of interactions. But when a solid solute feels the interactions in the solvent are also of similar kind, it can happily go and settle in those intermolecular spaces. That is the reason solubility will happen, or solubility occurs when they have similar intermolecular interactions. When the previous interactions between molecules, okay, when the previous interactions between the molecules, okay, and the new molecular interactions they are making in the solvent are almost similar, then they prefer to get soluble. Okay, obviously, if it can't sustain in a different intermolecular interaction environment going into the solvent, why will any solute prefer to go into that? It won't prefer. Okay, clear? So that is how solubility happens. This is a brief explanation of how a solid gets soluble into a liquid. Okay, it depends on what polarity. Okay, polar solids will get soluble in polar solvents. Non-polar solids will get soluble in non-polar solvents. Here for polar solvents, which liquid example I have taken here? Okay, H2O. Because we are talking about solvent being a liquid. Here, which liquid example I have taken here? Benzene. Okay, here I have taken benzene. My non-polar solvent here is my liquid, and what is the main example we have mentioned here, which is benzene, which is a liquid. So one thing is common here, our solvent is liquid, but it can be a polar liquid or it can be a non-polar liquid, okay, depending on the concept of like dissolves like, polar dissolves in polar, non-polar dissolves in non-polar. Okay, so this is a brief understanding about the solubility of solid in liquid. Now we have discussed about the nature of solute and we have discussed about the nature of solvent in solubility of solid in liquid. Now, okay, what in the first part I already told you, solubility depends on nature of solute, nature of solvent, both of them are done here. What are the next two factors I told you? Temperature and pressure. Now, how does the solubility of solid in liquid depend on temperature and pressure? Will it depend? If it depends, how? If it doesn't depend, there is no point only to discuss. Okay, so let us see that now. Before going into the effect of temperature and pressure on the solubility of solid in liquid, let us see a very important concept called dynamic equilibrium in a solution. Now, when we talk about solid and liquid solution, there is a very important concept called dynamic equilibrium. Now, when we talk about dynamic equilibrium, if you go back to your grade 11, you people have studied chemical equilibrium. So, a little bit of that concept comes here, but if you don't remember that also, there is no problem. I'll make you understand. Now, okay, solute plus solvent gives solution, we know, but here let us understand two different processes. Okay, let me take we are talking about a liquid solvent here. Okay, I have taken a liquid solvent. Okay, I have taken a liquid solvent. So here this is my solvent which is liquid. Okay, into this I am adding solute which is solid. Okay, solute which is solid. Now because this is a solid, I'll just represent it like this. Okay, I'll just represent it like this. Now what will happen when I have added a solute into a solvent? The solute slowly starts getting dissolved into the solvent. The solute slowly starts getting into the solvent and gets dissolved into the solvent. Now if you see here, okay, for example, see molarity is equal to number of moles divided by volume of solution. When the solid goes into the liquid, the solid goes into the intermolecular spaces in the solvent between the liquid particles. So the volume does not change. So the volume does not change. Okay, so the volume does not change. But if you see here, what is happening here? The solute is going into the solvent, volume is not changing, but the number of moles of solute will change. I'll keep on adding solute, so number of moles will change. Okay, now if number of moles changes, the concentration also changes. Okay, now when the number of moles of solute is changing, this is number of moles of solute divided by volume of solution. Now if the number of moles of solute is changing, the concentration also changes. When solute slowly gets dissolved into the solvent, the concentration of the solution will definitely change. Now the process of solute going into the solvent, in turn increasing the concentration of the solution, is called dissolution. What is dissolution? Okay, what is dissolution? It is a process where solute gets dissolved in the solvent, increasing the concentration of the solution. Okay, solute gets dissolved into the solvent, increasing the concentration of the solution. This is my dissolution. Dissolution means solute is going into the solvent, thereby increasing the concentration of the solution. Okay, now you keep on adding solute, now. Okay, you are adding solute is getting soluble. Now at the starting of the class I told you there is a certain saturation point, beyond which I cannot add solute. There is certain saturation point beyond which I can't add a solute. Okay, let us understand this in a very practical way, in a very simple way. Okay, when does this point reach, we will see. Now you kept on adding solute particles here now. Okay, you kept on adding solute, so you can see more number of solute particles in the solution now. Okay, you can see more number of solute particles in the solution now. When the number of solute particles are so many in the solution, they keep colliding with each other. they keep interacting with each other. Now, when a solution reaches the point of saturation, when a solution reaches the point of saturation means when no more solute can be added to solvent. When a solution reaches a point of saturation, there are so many solute particles in the solution, they internally collide with each other. Okay, they internally collide with each other. Now, when they internally collide with each other, what exactly happens here? Solute separates out. What happens? Solute separates out. Okay, initially what was happening? I was adding solute was getting soluble into the solvent, the concentration of the solution was increasing. This keeps on happening till the solution becomes a saturated solution. Now, after the solution has become saturated, what will happen? The solute particles will keep on colliding with each other, and solute particles will separate out. Means what? Now, the solute particles will become like small bunches, okay, and they get separated out. Now, this separation, what do I call it as? This separation I call it as crystallization. This separation, what do I call it as? Crystallization. So, dissolution process keeps on happening, increasing the concentration of the solution. When the solution becomes saturated, the solute particles keep on interacting with each other and they separate out from the solution, which I call it as crystallization. So, dissolution will happen. After reaching the saturation point, crystallization also can happen. So, what is crystallization here? Let us define what is crystallization. After the solution becomes saturated, the solute particles keep interacting and separate out from the solution. Okay, after the solution becomes saturated, the solute particles keep interacting and separate out from the solution. This process I call it as crystallization. Now you see here, okay, what did I tell you? Solute plus solvent. Okay, I will take my solute, okay, plus solvent. Okay, solute is getting dissolved in the solvent, and what is getting formed? Solution is getting formed. This process is what? This process is my dissolution. Okay, you are adding solute into the solvent, solute is getting dissolved, increasing the concentration of the solution. This process I call it as dissolution. Now what is happening now? What is happening? After reaching saturation point, the solute particles started interacting, and from the solution, the solute particles started getting separated out. Now, when solute is getting separated out, obviously solvent also will be separate. Solute got separated out. Now, from solution, solute and solvent are getting separated. Solute is going out as crystals. So, this process I call it as crystallization. Okay, this process I call it as crystallization. Solute plus solvent, solute getting dissolved in solvent, becoming a solution is dissolution. After saturation point is reached, solute interacting with each other and coming out of the solution is called crystallization. Okay, now when do these two processes takes place? Where do these two processes takes place simultaneously? They take place only in a saturated solution. Okay, only after the solution reaches the saturation point, these two processes keep on taking place. Now, what does it mean when I say dynamic equilibrium? What do I mean when I say dynamic equilibrium? Now, at the saturation point, okay, when the solution has become saturated, dissolution will keep on happening, crystallization also will keep on happening. Now, but why do we call it as dynamic equilibrium? We call it as dynamic equilibrium because, okay, and dynamic equilibrium is only possible for which kind of solution? A saturated solution. So, at dynamic equilibrium, rate of dissolution is equal to rate of crystallization. Okay, now when the rate of dissolution is equal to the rate of crystallization, now you people know, when you have studied chemical equilibrium in grade 11, when do you say chemical equilibrium is attained? We say chemical equilibrium is attained when the rate of forward reaction is equal to the rate of backward reaction. Am I right? Okay, now here what is the forward reaction? Dissolution. What is the backward reaction? Crystallization. Now when the rate of dissolution is equal to the rate of crystallization, I say the solution is in perfect dynamic equilibrium. That is what I was telling when I was talking about dynamic equilibrium in a solid liquid solution, where solid is solute and liquid is my solvent. Okay, this is the thing. Dissolution will take place, crystallization will take place when the saturation point is reached, and in the saturated solution, okay, the rate of dissolution is equal to rate of crystallization. Such type of condition, I call it as dynamic equilibrium, and dynamic equilibrium is only shown by saturated solutions. There is no point it is shown by unsaturated solutions, because it is still taking solute. Okay, it is still taking solute means it can still dissolve. It can still dissolve, so there the process happening mainly is dissolution, so there is no point of crystallization in a unsaturated solution. I can only talk about crystallization when the solute becomes too much in the solution, then they start interacting. So we cannot talk about any dynamic equilibrium when I am talking about an unsaturated solution. So this is about the dynamic equilibrium, okay, of a solution. Now let us see the effect of pressure and temperature on the solubility of solid and liquid. Let us see the effect of temperature on the solubility of solid in liquid. Now, when we talk about the effect of temperature here, we need to know about the Le Chatelier's principle, because this concept is understood well by the Le Chatelier's principle. Le Chatelier's principle you have studied in chemical equilibrium chapter in grade 11. Now here, when I told you people that this process of dissolution and crystallization is in dynamic equilibrium, so we can very well apply the Le Chatelier's principle here. Now I can't go into so much depth of Le Chatelier's principle, but I can at least explain you in a way to understand this particular concept. So according to Le Chatelier's principle, any physical or chemical process, any physical or chemical reversible process, it will try to maintain its equilibrium. Now if you see, we talk about equilibrium only if it is a reversible process. You people know that. Now when I am talking about this reversible process, it is in equilibrium. Now when I am talking about a physical equilibrium between these two processes, we can talk about Le Chatelier's principle, because Le Chatelier's principle says that a particular solution, all the components of a solution, they try their level best so that the equilibrium is not disturbed. They want to maintain that dynamic equilibrium. Now it's okay that they want to maintain dynamic equilibrium, but there are always some external factors, or for example, if you see here, for example, I try to increase the concentration of the solution. For example, if I try to increase the concentration of the solution here, okay, if I try to increase the concentration of the solution here, now you people know, if I try to increase the concentration of the solution here, means to the right hand side, if I try to increase the concentration of the solution here, what will happen? Okay, what will happen? If I try to increase the concentration of the solution, will this dynamic equilibrium condition in which the process is happening, will it want the solution's concentration to increase? Solution to increase in its quantity or concentration or anything? Does it want any change in the existing parameters by which it is there? It doesn't want. So when you are trying to increase the amount of solution, it will try to avoid it. Means what it will do? It will try to go backward. Because it doesn't want any increase in the solution. In the solution, that is the reason. What will the reaction do? It will try to go backward. If it goes backward, the extra whatever addition you have done to the solution, okay, it will go backward. It will get crystallized, so that the amount of solution will again come back to the normal state. Okay, So when I increase the amount of solution, the reaction prefer to go in which direction? It prefer to go in the backward direction because it wants to maintain equilibrium. So it doesn't want any change in the previous parameters responsible for the equilibrium. So it wants to nullify the increased change in the solution, or it doesn't want that increase, so it will go in the backward direction. Okay, I will do some other thing. Okay, now I will not deal with solution. I will interfere with the left hand side. I will interfere with the left hand side. Imagine I will increase the amount of solute. Okay, I will add 25 more grams of sugar. Okay, I will add 25 more grams of sugar. The system is already there in dynamic equilibrium. It doesn't want any addition of any amount, any disturbance regarding temperature, pressure. Any temperature disturbance the equilibrium doesn't want, any pressure disturbance it doesn't want, any amount disturbance, any extra amount on the left hand side and right hand side part it doesn't want. Now when you are increasing the amount of solute, now it doesn't want, so it wants the extra added solute to not to be there. So extra added solute it will try to take onto the solution side. Okay, now it will go. So what will happen? It doesn't want any increase in the solute concentration here. Okay, so to maintain the dynamic equilibrium, the reaction will go in which direction? Forward direction. Here the solution was getting disturbed, so to attain the equilibrium, the reaction was going in the backward direction. Now I interfered with the amount of solute, so the clear of the disturbance created, it will go in the forward direction. It will go in the forward direction. So here in which direction will the reaction prefer to go? In the forward direction. In the forward direction. So any disturbance you are trying to create on either of the sides, okay, what will the equilibrium try to do? It will be like you are creating a disturbance. Now I will adjust myself either forward or backward so that your disturbance does not affect my equilibrium. Okay, so that your disturbance does not affect my equilibrium. That is the reason when I made a disturbance here by increasing solution, it is going in the backward direction to release that extra burden. When I am increasing the amount of solute on this side to release that extra burden, it is going in the forward direction. Ultimately, it will try its level best so that the reaction maintains the dynamic equilibrium where the rate of forward reaction is equal to the rate of backward reaction. Here, the rate of dissolution should be equal to the rate of crystallization. Okay, this I have talked in general in terms of amount. Here our focus is on what? Our focus is on talking about the effect of temperature on the solubility. Now, how should I apply Le-Chatelier's principle? Okay, here for the effect of temperature. It is very easy, please try to follow. Now you have two types of reactions, exothermic reactions and endothermic reactions. So the effect of temperature on the solubility of solid in liquid depends on whether the dissolution is exothermic or endothermic. Means what? I will tell you. Solute plus solvent, okay, gives solution. Okay, if the reaction is releasing heat. If the reaction is releasing heat, what type of reaction should I call it as? Exothermic reaction. What type of reaction will I call it as? Exothermic reaction. Delta H is equal to negative. Whenever there is release in heat, the change in heat energy will be taken as negative. Now here, let me think. Okay, solute plus solvent is giving forming solution. Okay, and this is dissolution and crystallization will happen. Okay, when the saturation point reaches. So this is in dynamic equilibrium, all that I have explained. Now this process is releasing heat, so I am calling it as exothermic reaction. Delta H is equal to negative. What is one more possibility? Solute plus solvent gives solution. Okay, gives solution. Okay, here I have to supply heat for this reaction. For solute plus solvent, okay, for solute plus solvent becoming solution and solution coming back, in the form of crystallization, solute coming out, okay, this dissolution and crystallization process. For this dynamic equilibrium to be there, to be existing, to be achieved, or for these reactions to take place, I need to supply heat. I need to supply heat. Whenever you need to supply heat for any reaction, that reaction I call it as what? Endothermic reaction. I call it as endothermic reaction where delta H is equal to positive. Okay. Very simple. Reactions where heat is released is exothermic, delta H is equal to negative. Reactions where heat is absorbed is endothermic, where heat is absorbed, so delta H is equal to positive. Now, will the effect of temperature be different on exothermic and endothermic reactions? Definitely yes. And that we'll understand through Le Chatelier's principle. Now see this reaction. Okay, for example, if I increase the temperature. Okay, for example, if I increase the temperature. Now, in exothermic reaction, okay, heat is released to the right hand side. Okay, heat is released to the right hand side. Now you see, when the temperature is increased, now if I increase the temperature of this particular system, okay, what happens? The heat here will be more. Okay, temperature. Okay, now temperature is what? Temperature is the measurement of heat. So when I increase the temperature, the heat produced here will increase. Now the dynamic equilibrium doesn't want to get disturbed. The dynamic equilibrium doesn't want to get disturbed. So what will happen? What will happen? The reaction will go in which direction? When I increase the temperature, the reaction here I have increased heat, the equilibrium doesn't want to get disturbed. So to nullify the increase in the temperature on the right hand side, the reaction will go in which direction? Backward direction. When the temperature is released, the reaction will go in which direction? The reaction will go in backward direction. Now when the reaction is going in the backward direction, okay, you tell me, forward is dissolution, backward is crystallization. Now you tell me, when the reaction is going backward, which process is taking place? Crystallization is taking place. Now when the crystallization process is taking place, will the solubility decrease or increase? Getting soluble means what? Solute going into the solvent, and solution concentration increasing is dissolution. Crystallization is what? The solute which is soluble is coming together and getting crystallized out. So when the reaction is going backward, will my solubility increase or the formation of solid crystallization will increase? Crystallization will increase, because backward reaction is crystallization reaction. When from the solution solute is getting crystallized out, I say the solubility is decreasing, because solubility is solute going into the solution, but here the reaction is going in backward direction. So I can say solubility decreases. Okay, I can say the solubility decreases. Clear with this? So when I increase the temperature, the reaction to the right hand side, the heat is getting increased, the equilibrium is getting disturbed. So to nullify that change, the reaction will go in the backward direction, which is crystallization. So the solubility, what happens to the solubility? The solubility decreases. Now let me take other condition. Temperature is decreased. Now here what do I do? When I decrease the temperature, the heat liberated also decreases. Now previously, how much ever heat was needed for the equilibrium to be existing, that much heat was there. Now when you have decreased the temperature, the amount of heat got decreased. When the amount of heat got decreased, now I again told you here, decrease in heat I don't want. I want how much is needed. Decrease in heat I don't want. So to increase the amount of heat here, and again to establish the equilibrium condition, the reaction will go in the forward direction. So in which direction the reaction will move now? The reaction will move in the forward direction. Now you tell me, when the reaction is moving in the forward direction means what? Dissolution is increasing, so the solubility increases. So the solubility increases. So for an exothermic reaction, when I increase the temperature, solubility decreases because the reaction goes in the backward direction. When I decrease the temperature, the reaction goes in the forward direction, whereby the solubility increases. So can I say, for the exothermic reaction, temperature is inversely proportional to solubility of solute. Okay, solubility of solute in the okay, exothermic, whenever you increase the temperature, the dissolution process gets slowed down, so the solubility decreases. So temperature is inversely proportional to the solubility of solute in that particular solid. Now when I have taught this, I think this part will become very easy for you people. Let us do this. Now in this I am supplying heat, so heat is absorbed, so the heat factor I have on my left hand side. Now here if I increase the temperature, so there is an increase in temperature in the left hand side. It doesn't want, it wants the existing equilibrium temperature only. It doesn't want any the change or increase in temperature here. So to let off that heat, the reaction will go in the forward direction. Here I am increasing heat to get off that burden of that extra temperature or heat. The reaction will try to go in the forward direction. So the reaction, don't by heart, this is a very easy concept. The reaction goes in the forward direction. When the reaction goes in the forward direction, which process is taking place? Dissolution. So the solubility of solute in the solvent increases. So I can say solubility increases. Okay, now I can take the other case. Temperature decreases. Now I am reducing temperature, so it is on the left hand side. Now when I see the reduce in temperature on the left hand side, equilibrium says that no, my equilibrium is getting disturbed. There is a decrease in temperature. So please backward reaction. Okay, backward reaction, so that I can at least get some heat back. Okay, so the reaction, what will happen? The reaction comes in the backward direction because there is a decrease in the heat or temperature on the left hand side. So to get back to the normal equilibrium temperature, the reaction will try to go in the backward direction. Now the backward concept is what? The backward direction process is what? Crystallization. So whenever I am talking about crystallization, I say the solubility is, what happens to the solubility? The solubility decreases. So in the endothermic reaction, when I increase the temperature, the reaction goes forward, solubility increases. When I decrease the temperature, the reaction goes backward, crystallization is preferred, so solubility decreases. So overall I can say in an endothermic reaction, temperature is directly proportional to the solubility of solute in the solvent. Okay, this is how the temperature affects the solubility of solid in a particular liquid solvent. Here, what is the main concept we are applying here? We are applying Le-Chatelier's principle. Okay, and I have explained you how does the temperature affect an exothermic reaction and how does the temperature affect an endothermic reaction. When it comes to exothermic reaction, as I increase the temperature, the solubility decreases, and vice versa. When I come to the endothermic reaction, as I increase the temperature, the solubility increases. Okay, so this is the effect of temperature on the solubility of solid in liquid. Now, when I talk about the effect of pressure, okay, when I talk about the effect of pressure, what should I talk about the effect of pressure here? Will pressure really affect the solubility of solid in liquid? Will pressure really affect? Will pressure really affect the solubility of solid in liquid? It will not affect. Will it affect? For example, I have taken a liquid. Okay, I have a solid here. Okay, I have a solid here. Now, if I apply pressure, okay, will the solid get dissolved in the liquid? No. Can you compress solids? No. Can you compress solids? No. In solids, the intermolecular distance is very less. They are very tightly packed. They are already very tightly packed. You cannot compress the solid. When you cannot compress the solid and do any change in the solid, how much ever pressure you apply here, it will not affect the solubility of solid in liquid. So from now, if anyone asks, does pressure affect the solubility of solid in liquid? No, the pressure will not affect the solubility of solid in liquid because the solids are basically incompressible. So there is no effect of pressure on the solubility of solids in liquids because solids are incompressible, and the pressure you are applying will not show any effect on the solid getting compressed or changing something and getting dissolved in liquid. This process cannot happen. So pressure has no effect on the solubility of solids in liquids. So temperature I have explained. When talking about pressure, it does not show any effect on the solubility of solid in liquid. Whereas temperature, it will definitely show the effect on the solubility, and that also depends on whether it is exothermic and endothermic reaction. Because heat factor is very important in these reactions to take place. When you come to pressure, I clearly told pressure will not show any effect, because how much ever pressure you might apply on the solid being incompressible will not get affected, and its solubility, its particle movement will not get much affected because of the pressure you are applying on the solid. So today I have to discuss about the concept of solubility, and I in detail discussed about the solubility of solid in liquid. How does the nature of solute and solvent affect the solubility of solid in liquid? How does the temperature affect the solubility of solid in liquid in both exothermic and endothermic reactions? And I also told you pressure will not show any effect on the solubility of solid in liquid. Hope you understood the session and you loved the session. Okay, in the next class I'll be teaching you the effect of solubility. Okay, or I will discuss about the solubility of gas in liquid, a very major law we are going to discuss, and that is our Henry's law. Okay, so keep watching till the next session. Bye.